I'm asking you a question. So what's this? What have I just put up on the screen? Blah, 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 right? That's what I thought you said, okay? And this is, we've been talking about modeling strategy, and there are basically three stages: variable specification, interaction assessment, confounding with precision, confounding essentially followed by precision. And we illustrated, one of the things we did, we spent most of the time last class illustrating this strategy with this MRSA data set, where the exposure variable was previous hospitalization, the outcome was whether somebody got had MRSA or not, and there were three control variables: age, gender, and PAMU. And this was a summary table that described the all possible subsets approach, which I was been saying is probably the best approach, or the ideal approach that you might want, that you consider using to come up with the best model or to decide on the best model. And what you basically, and now in this particular case, if you remember, we started off with a model that allowed for product terms. It allowed for interaction of exposure with each of these covariates, age, gender, PAMU, and when we evaluated interaction using either a chunk test or backward elimination, what did we find? We found there was no interaction. So that meant that we could start with a model that didn't have any product terms, and it had the exposure variable and the gold standard model, the model that considered everything that we decided to measure and decided to worry about as possible confounders. So we had those three variables, age, gender, and PAMU in the model. And then we considered all possible subsets, and we basically said, okay, the gold standard model is the one that has in some sense, the best answer for the odds ratio, because it controls for everything on our list, that we're worried about. And then we're going to consider all possible subsets and see which subsets, if any, give us an odds ratio that's as close to the gold standard one as possible. And we decide how close is close according to some percentage rule. And one of the commonly used rules is the 10% rule. Could be a 15 or 20%, but I use the 10% rule. A lot of people do that. It's not, carved in stone. But anyhow, when you use the 10% rule, the only variable other than the only model other than the gold standard model that competes with the gold standard model is the one that drops gender. And that gives you an odds ratio within 10%, and all the other possible models give you odds ratios that are more than 10%. So if you use the 10% rule, you only have one competing model. And then the next question is, okay, I've got these two models. How am I going to decide between them? And the answer is, we're going to look at precision. And the way we're going to do that is we're going to get the confidence intervals for just the two models we're competing. And we can get it for the other models, but we don't really need them for the other models because we've narrowed it down to the gold standard model and this other model as the two possible models. And we get the confidence interval, and then we could either look at the confidence interval width or the confidence interval ratio. And when you're dealing with a logistic model and you're dealing with a ratio measure, like an odds ratio, as you measure effect, the usual way to decide on precision is using the confidence interval ratio, which is the highest value in the confidence interval divided by the lowest value. And when you look at it doesn't matter even if I did the width in this case, but when you look at the confidence interval ratio, it looks like, yeah, you gain some precision by dropping gender from the model. You control for confounding by dropping gender from the model, and you gain a little precision. So one might argue of these two models, the model that drops gender is better because it does you at least as well as the gold standard as far as confounding and gives you a little bit better precision. So that was sort of the idea that maybe that's the best model. However, at the same time, one might argue on another side of the coin in terms of how much precision do you really gain if you drop gender? And if you don't gain much, now how much is much, how much is a lot of precision is debatable. It's sort of subjective. And if you decide, for one reason or other, that you haven't gained enough precision, very much precision, by dropping gender, why drop it at all? The main reason for dropping it, the safe thing to do, is control for everything. And if you If you drop it and you gain some, but you don't gain very much, you might as well say, let's control for everything, because then you're doing what you originally set out to do. You're not dropping a variable that may cause you some problem in interpretation or public relations or something when you describe your study. So that's the idea behind the all possible subsets approach. Okay, and this was the idea of what happens in this nice case. You had no interaction, okay, because we found in this model that there was no interaction. So the last thing we did before we broke before we ended the class last time was we said, well, what happens if it turns out that and that's what we looked at. Well, what happens about what if it turned out, even though it didn't happen in this case, what if it turned out that there really was interaction? We found that we needed to keep a product term. So that was sort of the last couple of things we did, right? Isn't that what we did? Were you here? Yeah, I was here. So we considered this model, which had a product term. Okay. Now, the problem now is when you have a product term, could have more than one product term. When you have at least one product term, the odds ratio for the model that has all the variables in there, including the product term, is no longer a single number, e to the beta. It involves the effect modifier. The formula for the odds ratio involves the effect modifier. So for this particular model, the formula for the odds ratio for this model, which is now your sort of gold standard model for this example where there's interaction, even though there really wasn't, but I'm sort of pretending that maybe there was. This is the odds ratio formula for this model. And that means you don't get a single odds ratio value. The odds ratio will vary depending upon the effect modifier, and the effect modifier is age. So you're going to get different odds ratios depending upon what value of age you're going to use. So if you want to ask the question, is there confounding? Well, first of all, you can't drop age, right? You can't drop age because age's got to stay in the model. It's an effect modifier. The only two variables you can consider dropping is gender and PAMU. That's what we did at the end of the class last time. I'm just trying to go over it sort of fairly fast, but I'm trying to go over it here. And so if we just use the gold standard model and don't drop gender or PAMU, that's the formula for the odds ratio. But if we drop either gender or PAMU or both of them, this is still the formula for the odds ratio because it involves the exposure variable coefficient and the coefficient of the product term that involves the effect modifier times exposure. So that's still the formula. So the question now is, it's the same question. Does the odds ratio change depending on whether you drop one or more variables? But now we're not talking about an odds ratio, single odds ratio. We're talking about tables of odds ratios because we're not talking about a single odds ratio changing. So to illustrate that, I said, well, look, suppose we consider different values of age. That's the effect modifier. Well, if we plug different values of age into that odds ratio formula, we'll get a bunch of different odds ratios. And for the gold standard model, we'll get if we have 5 ages, we'll get 5 different odds ratios that will reflect the fact that age is an effect modifier. The odds ratio varies with the different age values. Now, if we decide to consider confounding and we drop any one or more of the variables, gender or PAMU or both of them, then we're still going to get a table of odds ratios if we drop one or more. But now if we ask the question, does the odds ratio change? We're not asking whether a single number changes. We're asking whether a table of odds ratios change. That's what I've been saying. Okay. So I gave you an example on this slide to sort of illustrate that. Okay. And I said, well, suppose it turned out that for the gold standard model where we kept gender and PAMU, we didn't drop anything. We also have age in the model because it has to stay in the model. It's an effect modifier. Suppose it turned out for 5 different choices of age, we got these 5 values for the odds ratio. We plug in the different age values and we go e to the beta hat plus delta 1 hat age and we get these 5 different odds ratios. Well, that's the table of odds ratios for the gold standard model. Then what happens if we drop either gender or PAMU or both? Well, we'll have 3 other tables of odds ratios to consider. So this is the one that drops V3, this is one that drops V2, and this is the one that drops both of them. Okay? And these are the three tables. And if you're going to ask the question, is there confounding, what you're going to say is, does the table of odds ratios that I get when I drop one or more variables, does that meaningfully change from the table of odds ratios for the gold standard? Okay? It's the same idea as if you didn't have interaction, it's just it's more complicated because now you have a table of odds ratios. And so what you have to do is, now it's more of a problem because you have a table, you have a number of odds ratios to look like. It's more subjective. Now, I'm just trying to give you an example where it's pretty clear-cut what you do, but you might not necessarily get something as clear-cut as this. So I don't know even whether it's clear-cut, but in any case, if you look at the table for the gold standard and the table when you drop V3, and you look at for each of the different age values that are chosen, the odds ratio when you drop whichever V3, whichever one that's PAMU, the odds ratio is almost the same as the odds ratio in the gold standard. It's not exactly the same, but it looks like if if you think about it, is the 5.4, is that 10% different from 5.2? You're asking the same question, but you're doing it 5 times because you've got these 5 different age values. Okay, and it looks like that these numbers, when you drop V3, aren't meaningfully different, 10%, whatever you want to call it, from the gold standard. So it looks like you could argue that, yeah, I can drop V3 and still control for confounding because I'm going to get the same answer as the gold standard model. Okay, that's what I'm saying. So that's fine. Now I look at the next situation where I drop V2, and I notice that, for example, in the first age value, the odds ratio is 9.2. That's a lot different from 5.2. It's a lot more than 10%, as is the 9 here and the 6.2. So you could argue that the third set of odds ratios, taken collectively, which is what you have to do when you have interaction, taken collectively is meaningfully different from the gold standard. So you can't consider this model, which drops V2. V2 is gender. Can't drop gender in this particular case. You can't use this model, but maybe you can use this model, which drops PAMU. And then you look at the model which drops them both, and you see again these 5 odds ratios are more or less collectively meaningfully different from the gold standard set of odds ratios. And so it looks like you can't use this model either. So you're down to these 2 models. Okay? With me? Down to these 2 models. Okay, then what do? Well, you've decided that I can either use the gold standard model, but now I have interaction, or I could use a model that drops the variable PAMU. How do I decide between the 2? Well, again, I've dealt with confounding. The next thing I do is precision. And so what do we do next? We deal with precision. And now when we're dealing with precision, we're talking about a table of confidence intervals, not a table of odds ratios. But if we decided age is going to be split up into 5 age categories, we're going to talk about 5 confidence intervals that we're going to compare, and we're going to have to compare. Now we've got to narrow it down to 2 models. And what we do is we look at the confidence interval for the gold standard model, the set of confidence intervals. We look at the set of confidence intervals for the model that drops PAMU, and we compare these 2 sets of confidence intervals, and we ask the question, do we gain precision by dropping the variable that we dropped? In this case was PAMU. Do we gain precision? Well, we certainly gain it here. We gain it here. Well, we don't gain it here, but it's not that much of a difference. We gain here and we gain here. And this looks like pretty much a fairly big gain, a substantial gain in precision, although, again, how much of a gain is still somewhat debatable. But based on these data, based on what I'm showing you, again, this is hypothetical, but based on this, you would probably say that the best model is not the gold standard model. It's the one that drops PAMU, and it's a model that involves interaction because we did interaction assessment, as a second stage in the strategy. So that's the idea. So when you have interaction, it's just more complicated. You have to deal with tables of odds ratios. And there's more subjectivity. The more interaction variables you have, the more product terms you have, the more complicated these tables look like. If you had 2 effect modifiers, age and race, then you have to sort of consider categories of age and race together, and you'd get a table that's it's a more complicated table. And you'd have to compare it for the gold standard model and for other subsets. And you might decide, after all was said and done, is that if you had too many interaction terms that had to stay in the model, you might say it's too subjective to try to decide on dropping any other variables. And you might say, well, I'll just keep everything in there. I won't try to drop anything as either non-confounders or variables that aren't dealing with precision, because I can't really make a clear-cut decision because there's too many tables to have to worry about to compare, to decide collectively. So that's one thing that a lot of people do. They might say, in the presence of interaction, I won't even assess confounding and precision. I'll use the gold standard model. But that doesn't mean you can't try. That's what I've tried here. I've said, well, if you do try to look at confounding and interaction, you might get a better answer than the gold standard model. So that's where we're at in terms of what we've now done so far is we've talked about a single exposure variable, and we've talked about no interaction and interaction and how to come up with the best model. Now, one of the things I started to talk about, and I did talk about a little bit, is I said, well, in the case of going back to to this thing, well, going back to even the model where we had no interaction, going back to this table where you're doing the all possible subsets. You remember I said something like, I talked about, well, what if it turns out instead of 3 variables, well, you're controlling for, suppose there were 10 variables or 15 variables, okay? And I said, well, you can still use the all possible subsets approach. It's just a lot more subsets to do. You remember we talked about that? Okay, so there's a lot more subsets to deal with. Now, that doesn't mean you can't use the all possible subsets approach. It's just, I mean, if you spent hours and dollars collecting your data, and you got 10 variables to worry about, maybe it's still okay to do the all possible subsets approach. It's just more time, but time is either money or importance in terms of what you're doing, so you might do it anyhow. And as I said last time, the computer's doing most of the work. Once you decide what the model is, regardless of which one of the all possible subsets, even if you have 10 variables, the computer's doing the work of fitting the model. You're not doing that. So you're using a program to do that kind of work, and then you're just getting the odds ratio for that model. Okay, so it's not that bad, it's still bad. But then I did say, well, are there any ways to shortcut the process? That's, can you cut down on doing all possible models and still get a good answer? And I described something to you as another alternative. And I'm going to talk about that again today. And what I'm going to do now is get out of this thing and talk about the next set of slides I have, which has to do with the issue of options for assessing confounding. Okay? So that's what I'm talking about. Okay? So if you brought your computer or your notes with you or something and you want to follow, that's what you're going to follow. And I made one small change in this, but I'll tell you about it when I show it to you. It's not much, and I wrote it down and I changed it even on the Blackboard. So it's easy for you, one small change. But now the whole idea of this topic is, well, what happens if you want to avoid having to do the all possible subsets? Is there a way you can still assess confounding and precision and still come up with a reasonable answer, particularly confounding, because that's what I'm really talking about here. Confounding is the biggest problem with the all possible subsets. Once you narrow things down, maybe it's not going to be that bad if you narrowed it down to 2 or 3 models. But once you're doing the so here's a list of choices. One of the choices is, we just talked about that, the all possible subsets approach. Another choice is the thing we talked about briefly. We'll talk about it again now, last class. Backward elimination of potential confounders using statistical testing with a check for confounding. That's what I talked about last time. Now, I don't know if you read the words. It is English, I don't know. But sometimes you read the word, you're not sure what that means. And, so we'll talk about that. And then there's a third approach called backward elimination of potential confounders using a change in estimate approach. This is a backwards approach. This is like starting with your gold standard model and dropping variables, but not dropping it, but not using a statistical test to drop them. Drop variables according to some kind of change in estimate criteria. Okay, and I'll explain that. I'm going to explain that. Okay, but and then there was this paper that came out. I don't know. I may have mentioned. I'm not sure if I remember the date. It might have been the mid-1980s. By these two fellows, and they had sort of an interesting point that I'm going to mention, but it's sort of, there's some debatable issues here, so I'm not going to really focus on that as something that you have to really know, but it's nice to know something that somebody said that might be a little interesting to talk about, but maybe not. I mean, if you don't really have to do it for an exam, who cares, right? So, but I think there on one of the, you're going to get, the midterm is October 1st. Midterm 1 is October 1st, and you're going to get some practice exercises, not next week, but, well, at the end of next week. Practice exams. And I think one of the practice exams may have a question about this Robinson and Joule thing. So don't worry about it, because you're not going to get a question like that on this one, okay? But anyhow, let's talk about these things. Well, all possible subsets, we just did this, okay? You run models, all possible subsets, you compare estimated odds ratios, select candidates, models that are within 10%. We just did all this, okay? And when we did all this, this is the extra slide I added. Have you seen this slide before? Well, that's what we started the class with. This is just the same slide. I'm just trying to say this is what we dealt with when we were doing the all possible. I wanted to put it into this PowerPoint presentation in addition to the previous one because I'm going to use it again, okay? I'm going to use it again for that third method, okay? So that's the all possible subsets approach, and we found out that these are the two models that you compare. In fact, what happened was we found that gender is the only variable that can be dropped to control for confounding, right? Gender is the only variable that dropped that gives you a model that's within 10. The odds ratio is within 10% of the odds ratio for the gold standard. So when we did the all possible subsets approach, we're down to two models, and we looked at the two models, and we looked at the confidence interval ratio, and this is just what we talked about at the beginning of class today. So you can decide to use the gold standard model by saying I didn't gain that much precision, or you could decide to use the model that drops gender if you said, well, I gained precision at least a little bit, and maybe that's better. Debatable. Lots of things are debatable. Okay. And there's not a lot of completely right answers in anything you do when you're doing modeling or any kind of analysis, and there's a lot of people who will argue somewhere or other in the literature or somewhere else. Okay, now let's look at the second one, the standard backwards elimination p-value based approach. That's the thing I gave you an example of. And this approach says drop the least significant, the highest p-value above whatever your alpha, your significance level, v variable from the gold standard model. Rerun the model and keep dropping v's, because I'm assuming this, you're dealing with confounding and there's no interaction. So you only have v's, you don't have e-v's. You know, product terms. It's more complicated if you want to deal with this confounding assessment when there's interaction. We already talked about it. You have to deal with tables. More complicated. You drop the least significant v variable. You rerun the model and keep dropping v's until you only significant v's remain. And this approach also applies to models containing interaction terms, but it's more you have to deal with tables. That's what I was just saying. Now, I gave you this example. I said suppose you had 10 variables that were potential confounders, not 3 like we had, just like I was saying just a few minutes ago. And you were using this method. What you do is you do what's called backward significant testing. So what variable do you drop first? You have E and 10 V's. Which V do you drop first? The one that's the least significant, right? How do you do that? Well, you fit the model that has all 10 in there, and you're either going to use a wall test or a likelihood ratio test to make that decision. Now, which test should you use? The likelihood ratio, because it's better. Which could you use? You could also do the wall test, but you might not get the same answer, but that's sort of easier to do. So a lot of people try it one way, but it's better to do the likely ratio. But if you're using the wall test, it's sort of easier, so I'm going to talk about it. If you're going to do the wall test and you fit this model, which had 10 V variables and 1 E, and the single E variable, which variable are you going to drop? Which of the V variables are you going to drop? The one you're going to get a bunch of wall statistics for each one of those V's, okay? And the wall statistics corresponding to that, you're going to get a p-value, right? So the p-value that's the highest is the least significant one, right? Now, if that highest p-value is less than 0.05, what does that mean? The least significant one is significant, right? If the highest p-value of an all 10 is still significant, what's that going to tell you about dropping variables? You don't drop any, because even the least significant one is significant, so you're stuck with this model with those 10 variables. So this approach, this backward elimination approach using statistical testing would say, well, you don't drop anything if the least significant one is significant, but if the least significant one is not significant, you drop it. And then what do? You have a reduced model that drops that variable, and then you go to see with that reduced model what's the least significant, and you keep doing it until you find a model that you can't drop anymore, because everything in the model, when you get to a certain stage of dropping variables, that model, you can't drop any more variables. So are you done when you get to that point? Well, this says I'm not finished here, because I then say, then you have to compare the odds ratio in the model resulting from backward elimination to the gold standard odds ratio to see if it's within 10%. So let's say, this is what I mentioned last time, let's say you start with 10, you do backward elimination, and you get down to 3 V's. So you now only have 3 by dropping a bunch of other V's, one at a time, going backwards. And now you have E and 3 V's, okay? And now you want to say, am I done? Well, what you have to do, if it's a no interaction model, what's the formula for the odds ratio if the E variable is a 0, 1 variable? It's E to the beta. So you compute E to the beta for that model that has the 3 V's in there, and you compare that E to the beta to the E to the beta in what model? The gold standard model. And when you ask, is the E to the beta in the reduced model after backward elimination, is that within 10% of the gold standard E to the beta? And if it is, then you know by doing this backward elimination and getting rid of some variables, you haven't done every possible subset. You've only done 7 tests or 6 tests to get to that point. You dropped 7 variables. Okay, you haven't done all possible subsets, but you do have a model that controls for confounding. Okay, and you've eliminated all these different possible subsets you consider. Is that the most precise model? Well, the only way you're going to know that is that more precise than the gold standard model. How are you going to figure that out? Well, one way is you get the confidence intervals for those 2 models, just like you did before, but now you're only down to 2 models. The one that you get after you drop 7 variables, and the gold standard model, and you look and see whether you gain precision by dropping these 7 variables. Okay? That's what you do. But the caveat to all this is, what if when you get that, and I said this before, I'm just saying it again, what if you get down to these 3 variables, you dropped 7, you get down to these 3 variables, you look at E to the beta for the model with the 3 variables, and that E to the beta is more than 10% different than the gold standard. That means that model that you got down to 3 variables doesn't control for confounding, because it's giving you a different answer than the gold standard, a meaningfully different answer. So you can't use that model. So what do you use? Well, one choice is to use the gold standard, but you could always use that. But what's another way to go about it? And I talked about this. What you could do is, well, then you try some other models, and probably the model that you're going to consider first is the model that adds to the model that you have with 3 variables. The one was the last one to drop out. The last variable to drop out. You add that, now you have 4 variables in the model. And when you add that to the model, then you look at E to the beta in that model, compare it to the gold standard. Well, if the E to beta for that model with 4 variables in there is within 10%, then you have a model. You haven't done all possible subsets. You do have a model that controls for confounding. It wasn't the model with 3, but one with 4. And maybe it's, you've got good reason to use that model. And if you want to compare precision, you can get confidence intervals for each model. Now, there's another argument, and I think I mentioned this last time. You could argue that, well, maybe I don't even have to do the confidence intervals, because when I'm doing this backwards elimination significance testing, in a sense, I'm indirectly looking at precision. Because when I'm asking whether something's significant or not significant, I'm asking whether the variation or the variance is large enough for me to drop a variable. The variance is large enough, what does that mean about the precision? If you're going to form a confidence interval with a variance, that means the larger the variance, the wider the confidence interval is. So if you decide when you're doing statistical, you're not actually doing a confidence interval, you're using a statistical test to do it, so you're not really doing it directly. But you could argue that this backward elimination, in a way, is sort of looking at precision first before it's looking at confounding. It's not looking at it directly. So you can always look at it directly by getting the confidence interval. So that's that approach. Okay, you got the idea, and I've already now said it the second time. So I want to talk about the third approach, but if you want to, stop me, ask a question. So I'm looking at Timothy over there, but I don't know, you don't have one, right? So, okay, that's okay. I don't look at anybody. Okay, now this is the third one. The standard that's what I just talked about. We just went through this. Compare the odds ratio in the model resulting from backward elimination. If not within 10%, add non-significant V's back until the 10% rule is satisfied. And if within 10%, stop and assume you have the best model, and maybe continue to look at some of the other ways to do it, to consider some other models. But this is an alternative to the all possible subsets approach. I still like the all possible. Jonathan has a question. Is that right? Did you have a question?
When you have back the significant leap,
yeah.
According to the p-values,
you're adding back something that dropped because it was not significant, right? In other words, if you got down to 3 variables, you drop that variable right near the end because it wasn't significant by having it in the model. But now you're adding it back because if you left the model at 3 variables, you wouldn't be controlling for confounding.
But say you have to drop 7 and you get down to 3.
Yeah.
And then you find that it's more than 10% different, so you have to add some back.
Yeah. What if you add another one back and it's still more than 10% different? You add another one back. You might wind up adding everything back, and you're back to the gold standard model. You haven't done anything. That's possible. And then you're back to doing all possible subsets or one of these other approaches. But that's a way to shortcut the process and maybe still get a reasonable answer. I still prefer all possible subsets because it doesn't miss anything. It doesn't miss models that you might understand something about that you wouldn't see if you do this. This approach cuts things out, as does the next approach that I'm going to talk about. So the next approach is, let's see, standard backwards elimination. That's what we just did. And that was what happened. This is approach 2. This is what happened. You got for the MRSA data, the first variable to drop when you went backwards was gender. It was the only variable that you could drop when you were doing backwards elimination. And you couldn't drop anything else. So you wound up getting the same answer as the all possible subsets approach. It just turned out that way. It won't necessarily be the case. You only had 3 variables to start with, but that's what happened. Okay. So now let's look at the 3. That's what I wanted to get at, the 3. The change in estimate backwards elimination approach. So this is one where you're not doing statistical testing to decide on, to move backwards from your gold standard model. So what does that mean? Okay, so let's talk about what that means. Now, this is what I said here. Now, I'll tell you why I put that table in there. Considering the V variables one at a time, drop the least confounding, using this whatever rule, the 10% rule, V variable from the gold standard model, providing it is a non-confounder within 10% of the gold standard odds ratio. Now, just to see how that would play into, this is why I put this thing back in here. Look at this table. Okay. Now look, I got a lot of models in. This is the all possible subsets approach. Okay. Which one of these models, there's more than one, drops a single variable? Well, not this one. This is the gold standard. It has everybody in there, right? This one drops age. This one drops gender. And this one drops PAMU. So at the first stage, you only say, I'm going to make a decision which if I'm going to drop one variable at a time, and I'm going to drop the variable that's the least confounder, the one that contributes least to confounding. Which variable is that? Gender, right? You drop gender, no confounding, in terms of the 10% rule. You drop any one of these others, you know, either age or PAMU, and you get confounded. There's only one choice to drop. The only variable you could drop at this first stage is gender. Now, what if it turned out instead of a 10% rule, you were using a 20% rule, so it turns out that 5.274 was within 20% of the gold standard, and 4.34 was also within 20% of the gold standard. Now, based on this first rule here, which variable would you drop? Which of the variables, if we're dealing a 20% rule, which of the variables could you drop that's the least confounder? Gender, PAMU, or age, if we're dealing a 20% rule? It's still gender, because this is closer to the gold standard than this one is, even though that one also controls for confounding. So gender is the least of these that are it turns out there are two variables that are non-confounders here if you drop them one at a time. But one of them is better than the other in terms of this 10% rule. This one's better, it's closer. That's what it says. That's what this rule says. Okay? And what do you think? That's the first step. So the first step says, okay, at the first step, you drop the least significant one, not the least significant one, the least confounder. Okay? Then what's the second step? Well, in this case, it's not that big a deal. Now you know you're going to drop gender at the first step, right? That's what you've decided in terms of this rule. Okay? So what else can you drop? You can drop age, because you haven't dropped that yet, and you can drop PAMU, but you've already dropped gender. Okay? So look at these three models down here. This one has PAMU in the model, this has age, and this has... Which one of these models don't you want to look at? You don't want to look at this model. Why? You already dropped gender at the first stage. So you want to see, once I've dropped gender, can I drop one of the other variables? Then I've dropped two variables. This one drops two variables, but neither of them is gender, which we've already dropped. So at the second stage, I'm saying, okay, of these two models, which one is the least confounder? And the answer is this one, right? Dropping age. Age is the least confounder, right? But if we're using the 10% rule, can I drop age? No, because the 10% rule said I had to get something that was within, the range was something, it had to be within 4. It couldn't be, 5 was the cut point. If you had 5, it was too far. That's what we looked at before when we looked at this table within 10%. 5 was not within 10%. Of the gold standard, and it's not going to be even in this case. Okay, so if we're going to consider what to do after we've dropped gender, what's our answer? Can we drop any other variable? Can we drop either age or PAMU? The answer: we can't drop either one. So using this backward change in estimate approach, what's our final model? Without considering precision. It's the one that drops gender, which was the same model that we got from the all possible subsets approach or from the backward significant approach. No guarantee in a different situation you get exactly the same answers, but it turns out to be the same answer in this case. Now, what if it was instead of the 10% rule, it was the 15% rule or the 20% rule? Okay. So at the first stage you drop gender. What about the second stage? If you're doing a 20% rule to say whether you can drop any more variables once you've dropped gender. So what's the answer? Yeah, you can drop whatever it is with the variable here. You can drop age because that leaves PAMU in the model. You can drop age. And then you're still within 10%. Okay? So that's what the change in estimate approach looks like. It allows you to go backwards from a gold standard model and drops variables one at a time according to whether confounding is considered, one variable at a time. Okay? And if you want to still assess whether you gain precision or not, once you get down there, you can always compare the confidence intervals. You can always do that in addition to that. Some people use the change in estimate rule and they don't even bother with precision. And that's debatable, because then you're not using something you might want to take into account. Okay, so those are the three approaches. That's, you know, and this change in estimate approach also doesn't deal with this, doesn't deal with the all possible, it doesn't look at all possible subsets. You're looking at, I mean, in this case, I didn't look at all possible subsets because, well, it looks like I did because I started with these three, you know, I didn't look at all possible yet. I started with these three and then I dropped, I only considered this one. And once I did this one, I only considered these two. I didn't consider this one. So I didn't look at all possible subsets, but I only had three to start with, so I really didn't gain that much. If I had 10 variables I was starting with, the change in estimate might save a lot of all possible subsets to deal with. But again, that's a better, the latter, the all possible, is still a better approach. You got the difference here? I'm not sure. So what do you like? Well, I don't know what you like, you know. You might like not to have to do all possible subsets. But if you don't do that, you have to do one of these and you have to do it correctly. Okay, so that's what they are. Now, the only other thing I wanted to say was something about this approach. This is what the other approach is. But change in estimate approach, considering V variables one at a time, drop the least confounding variable from the gold standard model, providing it as a non-confounder. And then the second stage, rerun the model without the dropped V and keep dropping V's sequentially until only truly confounding V's remain. The only ones that are left are the ones that you decide are confounders. You're dropping non-confounders, one at a time. That's what it says. And what did I say? Either assume the model is the best model, you're done, or do something with precision. That's what I say down here at the bottom. And there's all sorts of room for people having an argument about. And it turns out, we just walked through that for the MRSA example, you get the same result. The only model that you deal with if you're using the 10% rule is the one that drops gender. So you're back at the, so now let me say something about Robinson and Jewell. I'm not going to say too much, okay? But I'm going to say something and then I want to go on to something else. And I better not say much because I got a lot of other stuff to do. When you learned about linear regression, last semester with Bob Lyles using Kleinbaum Cooper, these Morgenstern book. Okay, one thing you may remember he talked about is if you had a linear model, multiple regression, a linear model, and you had three variables you put in the model, and you found that two variables needed to stay in the model because they had to be controlled because you knew they were important variables and maybe you decided they were confounders in terms of linear regression. But the third variable wasn't a confounder. You decided it wasn't a good. Now, if you got linear regression and you're asking whether a variable is a confounder in linear regression, you're not asking whether the coefficient of that, the e to the beta changes differently from e to the beta in the gold standard model, because in linear regression, the gold standard model is linear. So the odds ratio that's not the measure of effect. Beta is the measure of effect. The coefficient itself is a measure of effect. But the point I'm trying to make is that if there's a third variable that it looks like you don't need to control for it for confounding, there is another reason why you might want to control for it. You got a variable like age. It's not a confounder, but it's a very strong predictor of the outcome. What do you think it might mean to put age in the model? Well, maybe even though you don't need it to control for confounding, it helps what? That's the other thing we're talking about. It helps precision. You put age in the model, you get a tighter confidence interval around whatever you're talking about, whatever odds ratio or whatever regression coefficient you're talking about. So for linear regression, that's what it says. It says in classical linear regression, the adjustment for a non-confounding predictive covariate results in improved precision. If you had a variable like age and it was a strong predictor, typically what happens if you put it in, you gain something more than just controlling for confounding. Well, it turns out this paper that was written, and it was called Some Surprising Results About Covariate Adjustment in Logistic Regression Models, they made this following statement. They say, let's see, do I have it here? In classic linear regression, the adjustment for a non-confounding predictive covariate results in improved precision, whereas such adjustment in logistic regression results in a loss of precision. That's what this says. So if you were doing logistic regression and you had three variables and you decided that two of them you had to control for because they were confounders, and the third one wasn't a confounder, okay? You decided it wasn't a confounder on its own or in any way to look at it, okay? If you controlled for it, if you added to the model, you'd lose precision. You wouldn't gain precision. You know, if you added age to the model in the linear regressions, you might gain precision because it's a strong predictor. Even if that third variable was a strong predictor, you would actually lose precision. That's what this said. So, I mean, for example, just to give you an example, here's the gold standard model. Suppose it turns out that three variables in the model. Suppose the following two models each give an estimate of the odds ratio within 10% of the gold standard, each one of these models. Okay. Now, I only have one variable in there. Okay. But what it means that if I just control for C1, I'm dealing with confounding. And if I just control for C2, but if I drop the other two variables, I'm in trouble. Okay. Now, one variable that's clearly not in either one of these models is C3. So what if I added C3 to either one of these two models? Either one of these two models, and I'm using this rule, what would happen? Would I gain precision or lose precision? I'd lose it because that's what this thing says, okay? Even though C3 might be an important predictor, that's what it says, okay? So, you know, now that's their rule, that's their thing. Now, I'm not sure whether this is truly true, because it might be that where such adjustment results in a loss of precision. I don't know whether they meant it always or whether more or less, in most cases, like the expected value is. So I'm not sure what they really meant there. And I'd have to reread, we would have to read the paper, or somebody would have to reread the paper. So I'm not sure whether that's true, so whether that's always the case. You know, and then I said, well, in any case, even if you had this rule and you wanted to determine between these two models, both of which control for confounding, how would you choose between these two models? That's what I said. Can you say whether model A or model B gives better precision than the gold standard model? Well, you can't. You just know that, you know, neither one of them has C3 in there. And which one is better? Which one of the two models is better? Well, I think you can say model A or model B gives better precision than the gold standard model because it doesn't have these other variables in there. It doesn't have C3 in there. But how can you say which one is better? So their result is nice. It's surprising, but I quit on that. Okay? So you're not going to get a question on that. Okay? Just want to let you know. Now, here's what I want to do now. I want to talk about another topic that's on our list that we don't have time to do everything on this topic. So I want to talk about it and start talking about it. And I don't want to talk about it too much because if you look at the schedule for the course, the schedule of what's supposed to be covered from one class to another, what was supposed to be covered today? You haven't looked at it. You should look at it because when you look at the schedule, you sort of know what should be being talked about, even though I might be behind, or we might be behind. The topic for today was supposed to be polytomous logistic regression, not what we're doing today. But we're behind. So now, here's the thing. Modeling strategy with several E's. That's what I'm going to talk about now. Up to this point, we've only dealt with one E. It was previous hospitalization in the MRSA data. Just 1E. Okay. What if you have more than 1E? What do? How is it complicated? It is more complicated. It's always more complicated. Okay. But there's sort of a strategy, or some alternative strategy. So let's talk about that. Okay. Well, first of all, I start off by saying I'm going to review the hierarchical backwards elimination strategy for single E. Well, I already did that. That's on this slide. Forget about it. Let's look at this slide. Okay. Now, there's a model on this slide. Now, the model has to do with the MRSA data. Okay. And I've listed the variables at the top of the screen. Okay. What have I done that's different from before? What's different? I now have 2 E's, not 1 E. I said, suppose you're interested in whether previous antimicrobial drug use or previous hospitalization or both in some way or neither are important predictors of whether somebody is resistant, is MRSA resistant. That's what the question is. Controlling for 2 other variables, age and gender. So this is different. It's different because this question now involves 2 exposures and 2 covariates. Now, what should be the question? I don't know what should be the question. You know, when you're doing a study, you have to decide what is reasonable to decide on the exposure variables and what's reasonable to decide on the control variables. Now, usually the way you decide on the control variables are variables you already know something about. There's already a little literature about. There's some conceptual understanding about. And the ones you consider exposure variables are variables you're interested in finding out something about you don't know that much about. So I'm supposing here that I don't know anything, not only is previous hospitalization, but I really want to find out something about PAMU, that I don't feel like I consider it a control variable. I want to use that as an exposure variable also. So now I have 2 exposure variables and 2 control variables. Now look at the model on this page where it turns out the V's, now there's 2 V's, there's 2 C's, age and gender. In this model, the V's and the W's are the same as the C's. Look at this model. What's different about this model than what we had before? Well, first of all, you notice I've written the 2 E's. There are 2 E's, not 1 E. So I'm trying to identify that I want to draw conclusions about whether either one or both or separately or together predict whether somebody gets MRSA. And I want to control for these 2 variables, age and gender. I'm just going to control for them as they are, but I'm going to call them V's even though I'm not making them more complicated. And now I'm going to consider, now what happened here? What happened here? What did I do here? I got product terms in the model, but I have 2 kinds of product terms, right? I've got E's with V's or E's with C's, and then I've got E's with E's, right? Well, it's 2 E's, so there's only 1 E with the other E, okay? So I've got E1 times W1, and W1 is age, and E2 times age, and E1 times gender, and E2 times gender. This is an interaction of the exposure with the covariate. Okay? But this is no longer an interaction of an exposure variable. This is an interaction of one exposure with another. It's a different model, right? Do we treat this model any differently? And well, it always depends, okay? But it makes sense to treat them differently because what you have now is a different situation. You have 2 different kinds of interaction terms, okay? Interaction involving one variable that's an exposure with a variable that's a covariate, and this is an interaction of one variable that's an exposure with another. This is a different kind of interaction. In a way, this variable, E1 times E2, is sort of like another exposure variable. I mean, there's E1, there's E2, and there's some combination of the 2 that might affect the outcome, but it doesn't involve a covariate. So maybe they should be considered separately. You get what I'm saying here? It's a different situation. So how do you do that? How do you deal with that? Okay. Well, if you consider the strategy that we talked about, the first strategy is you define the model. You know, the variable first part of the strategy, define the model. The second part of the strategy is interaction assessment, right? So if I was doing interaction assessment, what would I do here? Would I treat interaction all together, like it's one big party? You know, or do I say, do I consider one kind of interaction before I consider another kind of interaction? See what I'm saying? That's what I'm trying to get at, okay? And actually, there's different opinions about this, okay? And most people would tend to say, if I consider the fact there's two different kinds of interactions, what I might want to do is not deal with the EE interaction until I deal with the EVs or the EW interaction. Why is that? Does that make sense? I don't know. Think about that. You know, in other words, that's what most actually statisticians or epidemiology methods people would do. They wouldn't touch. They would consider interaction, but they wouldn't consider interaction about EE until I've dealt with the EWs in this model. Why is that? Anybody got an idea about that? Not Lindsay, because you were in the class last year. You can't. Okay. Any idea? I mean, the idea is this. You know, when we did the modeling strategy, when there was a single E, and there was no interaction of any kind, and we tried to decide what the best model is, we never touched the E until we dealt with the covariates. Isn't that true? We never addressed whether we needed those E's in the model, or the one E in the model, until we dealt with the variables we wanted to control for. So you might say, this EE variable is sort of like an E, so let's not touch it until we dealt with the covariates. Or let's at least not touch it until we deal with interaction among the covariates. That's an argument. You get into these kind of situations and there's debates on this thing. You know, there's points of view on this thing, but that's the point of view a lot of people take. Don't touch this interaction term until you touch these. Okay. Then there's a question, what do you do after you do that? But anyhow, this is one of the problems, one of the issues. And we're going to go through an example here. Now, look at this. What's this? What have I just done? I've destroyed your life here by putting this on the screen. All right? What's this? Well, this is the most general model that this is a special case of. So if you got several E's, this is really what you're dealing with. You know, and I just made it simple. But this is where it's bad. Okay? It's where it's bad. Okay, look at what's in this model. Now, it said logit P of X, so we know it's a logistic model, right? And we know it's logit P of X, so the way we've talked about it, it's a binary logistic model. Now there are variables in this model. There's an alpha, just like there always is in a logistic regression model. And what's this? What is it? What's this term? These are the E's in the model. It allows you to have more than one E. How many E's do you have in the model? Q, because that's what this value is. It says Q. If you had two E's, what would Q be? 2. Ooh. Okay? So that's the number, that's the E's. The V's, well, those are the V's. You decide you decide that in advance. Okay? So you got your E's, you decide in advance. The V's, you decide in advance. What are these? Well, these are the product terms of each E with each W that you want to consider as an effect modifier. And for each E, there's a collection of W's. So if you're talking about E1, there's a collection of W's. E2, there's a collection of W's. That's why there's a double sum. You know, it's more mathematically complicated, but you know, there were, if you look back at this, there's this sum, and there's this sum. Oh, well, that is, there's E1W1 and E1W2, and there's E2W1 and E2W2. So there's two sums in there for all possible ways of considering E times W's. And then there's the last one. What's the last one there? The last set of stuff. It's all the EE stuff. And the notation's a little bit, it says I can't be equal to J. Down at the bottom of this, it says this is an I, and this is an I prime, and I can't be equal to I. These are two different subscripts, and these can't be the same. You remember in this example, there were only two E's. So you could only have E1. What if there were three E's? What would it be? E1 times E2, E1 times E3, and what? E2 times E3. Would it be E1 square? Well, it could be, but that's not what I allow. I mean, it always could be that too. Then you're talking about another kind of E. But if you're talking about products among E's, you were just talking about, you can't have, it's all possible pairs of subsets, so it's different. Anyhow, that's the model. And all I've done is written out, these are the E's, these are the V's, these are the EW's, these are the EE's. That's the model, okay? So you look at this and you say, that's it, I quit, I shouldn't have been in this class in the first place, right? Things are getting really bad now, okay? Maybe they are, maybe they're not, but let's talk about how you would do it. Now, here's this general model, and I've got two strategies for dealing with this model, okay? They're alternative, they're debatable, and there's probably three others that are debatable, okay? Look at the first one. Look at the first two, the alternative one, alternative. The first step in both of these alternatives, alternative one and alternative two, is the same, right? Isn't the first step the same? Variable specification. Why is it the same? Because you should start out with whatever model you want to deal with in the first place. And regardless of your strategy, you define the model according to what variables you want. Variable specification. Okay. The second step says interaction assessment involving the EWs. That's in this one. What about this second step? So the second step in each of these two strategies is the same. That reflects what I originally was saying, that you shouldn't try to look at interaction about the EEs until you dealt with interaction about the EWs. So I'm being consistent in either strategy by saying, I'm only going to talk about covariates, whether they're effect modifiers, before I talked about interactions of one E with another, because that's more causal relationship type of thing than this is causal, but this is covariate stuff. And so that's the second one is the same too. Well, what about the third one? Third one's different. See it? What does the third one do? What's the third one on alternative one say? Well, once you deal with the initial model, and once you decide to deal with interaction like this, the next thing you do is deal with these interactions. Isn't that what that third step says? Okay? Now, what's the rationale for doing that? I mean, I did say something like, don't touch the E's until you dealt with the V's. That's not what this step is saying. This step is saying interaction comes precedent to confounding. That's what this step says. If you're gonna start reducing a model, consider whether you have any interaction terms before you start worrying about confounding. So once you deal with these interactions, then deal with this interaction. That's what this approach says. It's dealing with the modeling strategy that I laid out, which says variable specification, interaction, confounding. So this says, well, there's one kind of interaction and there's another kind. Let's deal with one kind first and let's deal with the second kind. Well, what about step 3 here? What about that one? What does that say? That deals with confounding before you deal with the interaction among the E's. That says, look, I don't want to touch the E's until I deal with confounding about the V's, because the E's are my main variables of interest. I don't want to touch the E's until I deal with confounding in the V's. That's what this step says. And then once you do this, then you do interaction among the E's. So these steps of 3 and 4 are switched around here. And then you look at the E's after you've done everything, and we need to talk about that too. So there's a reason for each one of these steps, and there's no necessarily right way, and there's probably 35 other ones, but these are the two ways that make sense to me to do it. Okay. Do you like one or the other? What do you like, Kevin?
I don't know. We haven't seen it.
You haven't seen anything. You just saw it. It's on the screen. No, I'm just kidding. You haven't thought about it, I think is what you meant. And you have to think about it a little bit, and if you think about it, you're still not going to know, because I don't know. I'm just telling you what the advantage here is interaction before confounding. This is confounding before you deal with E's. That's what this says. Deal with confounding, deal with covariates before you deal with your exposure variables. That's what the second one says. Okay, so now let's look at this. I'm watching the clock here. Let's look at this. Now first of all, I'm going back to this model. Here it is again. I'm going back to this simple model. It's going to be terrible. We could have 35 E's. We only have 2 E's. So if we can't figure it out with this, we're not going to be able to figure it out with more E's. Okay, so we got 2 E's, 2 V's, we got these 4 EW's, and we got an E1, E2. Okay. Now, suppose I said, which to check first, the EW's or the EE's? And I'm saying, if you check the EE's first, here's the model. If I decide to test for whether this is significant, then I'm not using either one of those 2 alternatives, right? If I decide to test for the EE in this model, those alternatives said wait on the EE's. So that's not right. So I have to do one of the others. If I check the EW's followed by the EE's, then I'm using alternative 1. If I check for the EW's followed by the V's and then the EE's, then I'm using alternative 2. So I have 2 choices. Will I get the same answer? No, not necessarily. You won't always get you never hardly ever get the same. So there's, hopefully if you got the same answer, you'd feel better. No guarantees. So again, this is one of these things that say, gee, what am I doing in this class? There's all sorts of stuff that's going on. Nobody knows. Even the instructor doesn't know what you're going to get. There are approaches to things, but you don't really know exactly what you're going to get. There's approaches and there's debatable stuff. I don't like this. I want to be in an area where it's chemistry. I put the thing in there, it blows up, or it doesn't blow, whatever. So, okay. So let's look at alternative 1. Suppose we do alternative 1. Okay, let's go through this thing. Suppose there's no interaction of any kind. No interaction. Well, let's say we did alternative 1, and which meant we did the EW's, and then we did the EE's. We did one interaction, then we did the next interaction. And suppose it turned out we found none of that was significant. This is what we'd be left with, right? Isn't that what we were left with if we found no interaction and we're doing alternative 1, which says interaction before we deal with confounding? Okay. Now, what do we do here? What do we want to do? The next step is, do we control for V1 or V2? Isn't that what we want to do? We got E1 and E2, but we're at this point in our strategy, do we drop V1 or V2? We don't touch the E's right at this point. That's what most people will say. Don't touch the E's until you deal with the variables you're controlling for. So how would you do that? Well, there's a lot of different ways you can do that. Let's look at one way. Look at this. Now, there are 2 E's, E1 and E2. They're like 2 different variables. They can have, one could be, well, one of them is previous hospitalization, the other is PAMU. I mean, they're 2 different variables. Okay, so suppose we say this. Suppose we say, well, look, if we're going to consider the fact that we have 2 E's, what about somebody who on the 2 E's they have on one E that person has got a certain value, and on the other E they have a certain value. So they're previously hospitalized. And they previously used antimicrobial drugs. So what's the value of these 2 variables on that person? 1, 1, right? But what if they have neither? 0, 0. What if they have 1 and not the other? It's either 1, 0, 0, 1, right? So we might say, since I got 2 variables, why don't we say, let's consider looking at the collection of those 2 variables and specify a person's value of those 2 variables, and then look at another person who has a different collection of values on those 2 variables. So we are looking at a comparison of 2 different people, but we now have 2 E's, we don't have 1 E, but that's a way of doing it. So there's a number of different ways of doing it, but what if we specify, look at what I said here. Suppose we do the following. Suppose, let's see, did I say anything over here? Suppose we decide to compare E1 equal to 1, E2 equal to 1 versus E1 equal to 0 and E2 equal to 0. What are we doing? What are we doing if we decide that's the key comparison we want to make? Well, some people might want to do that. There's a lot of different comparisons, but that's saying high versus low. Somebody who has both versus somebody who has neither. If there's nothing going on with both versus neither, maybe there's nothing going on with any other comparison. So you might say, let's focus on a particular comparison like 1 versus 0. Well, if it's 1 versus 0, and you remember the formula for the odds ratio in this model, the formula for the odds ratio in this model is you're controlling for these variables, given these are fixed. So the odds ratio is beta 1 E1 star minus E1 plus beta 2 E star minus E2, where E1 star is the value of E1 for one person, and E1 is the value of E1 for the other person. So for one person it's 1, and the other person it's 0. And for the previous hospitalization variable. And this is the PAMU variable, 1 versus 0. So if we plug in 1 versus 0 in this formula, what do we get for the odds ratio? Well, again, the odds ratio doesn't involve the V's. It's e to the beta 1 plus beta 2. That's the formula for the odds ratio. So if we want to compare high versus low, somebody who has both with somebody who has neither, we now have changed the problem from having two exposures and two different maybe odds ratios or all sorts of e to the betas to one formula for an odds ratio that we're focusing on, which is e to the beta 1 plus beta 2. That's a way to deal with this thing. Okay, that's not the only way, but it's one way to deal with it. Okay, now if we do this and we want to say, okay, that regardless of whether V1 and V2 are both in the model, that's gold standard. Neither are in the model, that's crude. One's in the model and not the other. Regardless of which one, the formula for the odds ratio is going to be, if we're comparing 1 versus 0, that's the formula for the odds ratios, e to the beta 1 plus beta 2. It's going to change depending upon whether both V1 and V2 are in the model, neither are in the model, and one is in the model and not the other. It's going to change. So then what does that mean? Well, that means it's sort of like, this is a no interaction model, but we actually are dealing with tables of odds ratios here. It's what we're doing. When we have two or more E's and we're trying to assess confounding, we try to do it this way, we're dealing with tables of odds ratios. We try to do it this way. So here's the table. If we're dealing with, if age and gender are both in the model, if V1 and V2 are in the model, then basically the formula is going to be beta, e to the beta 1 plus beta 2. That would be the odds ratio that would have them both in the model when we fit the model. If one of them is in and the age is in but gender isn't, then it would still be e to the beta 1 plus beta 2, but one of these variables wouldn't be in the model. So beta 1 and beta 2 might change because you're fitting a different model. You don't have all the same variables in the model. Beta 1 and beta 2 might change if you just have gender in the model, and beta 1 and beta 2 might change if you have neither of them in the model. So you'd get 4 different odds ratios, depending upon whether both of them are in the model, one of them's in the model, or neither's in the model. So what would you do with this? What would you do with this? In terms of deciding about whether there's confounding or not. What would you do? You look at what's the correct answer? The correct one is the gold standard one. And what you do is look at these other ones and say, do they change meaningfully, 10%, say, from the gold standard? Okay, that's what you're going to do, the same thing. So on the next slide, I did this. I took a guess. I said, suppose it turns out that this one is within 10%, but this one isn't, and this one isn't. Okay, then suppose that's what happened. Well, that means I've now narrowed the problem down. I've controlled for confounding. I've decided the two models after I control for confounding. And now I'm going to try to decide between a model that has age and gender in there as the two V's, or just gender in there, and I'm going to decide based on precision. So I'm going to get the odds ratio for this model, the confidence interval for this model, and the confidence for this model, I'm going to compare them, just like I did when I did only a single E. It's sort of like I'm changing it to a single E, but it's not a single E, it's two E's. But I'm saying, let's combine them. E1, E2 combined. One E1, E2 pair with another E1, E2 pair. That's a way of doing this. It's not the only way of doing it, okay? And because of time, I don't really have that much time to do everything here, okay? But that's what you do. Now, this is using alternative 1. What if you used alternative 2? I just described, I don't even know if you followed me on alternative 1, but let's look at alternative 2 here. Alternative 2. Now, suppose we're doing alternative 2. So for alternative 2, we start with this model, same model that we started with, same model that we started with. But alternative 2 says, again, that's the starting model. The second stage is the EWs. Suppose we found out after the EWs, it's a different thing. Suppose we found out there was no EWs. None of the EWs needed to be in the model. Okay? So at the end of that second part of the strategy where I've dealt with the EWs, I've gotten rid of all the EWs. Have I gotten rid of the E1 times E2 yet? Why haven't I? Because that's not the second stage. The second stage was only do the the EW terms. So I've gotten rid of the EW terms, but I still have this to worry about. Well, when I'm using alternative 2, what's the next step? Go back to this. Next step. Next step is confounding, not testing for the product term. That's the next step for alternative 2. So what do I do here? Whoa, where is it? This is it, alternative 2. Assess confounding precision. But now, you see, at this stage, if I want to assess confounding, I'm still asking the question, does V1 and V2, should I drop them? Are they confounders? Do I need them in the model or not to control for them? But now I haven't done anything about this yet, and I'm not going to do anything about this until I ask the question about confounding. So this product term is going to stay in the model. So for this situation, what's the formula for the odds ratio for this situation? What's involved in the what coefficients are involved in the odds ratio for this situation? What coefficients are involved? It involves this coefficient, what other one? This one, okay? Now suppose it turns out that I again wanted to compare 1-1 versus 0-0. 1-1 versus high versus low, just like I did for the previous situation, but this is alternative 2. Okay? Now, this would be the formula for the odds ratio. Do you believe me? That would be the formula for the odds ratio. 1-1 means it's, this is 1 versus 0, this is 1 versus 0, and this is 1 versus 0. 1 times 1 versus 0 times 0. So it's e to the beta 1 plus beta 2 plus delta 4. So in order to assess, if I'm using the second strategy, you have to decide which strategy you want. If I'm using the second strategy, again, I would, I'm now computing this as my odds ratio, but I'm still considering all the possible subsets of covariates to use. Should I have them both in there, just one in there, or neither of them in there? And I get 4 different odds ratios. They may not be the same 4 odds ratios I did when I dealt alternative 1. Okay, they could be different. I'm saying suppose it turned out that it was the same thing, and then that would mean you would be doing the same thing as I did before. But the idea is when you've got 2 exposures, or more than 2 exposures, the model's more complicated. You got 2 kinds of product terms. So the strategy is more complicated than that, okay? And it is 20 after 5, so what am I going to do? I got, so many more things to say about this. And if I spend the next class talking about this, what does that mean? Ooh, we're going to be so far behind, you're not even going to be able to be ready to take the midterm exam. So I got to... Maybe we can put her off until the end of November. No, we're not. So I'm going to stop talking about this, and I'm going to say a little bit more about this next time, but not much more. And then most of the next class is going to be on polytomous logistic regression. That's what most of the class is going to be. So you need to read about this. Chapter 8 in the logistic regression book talks about this and gives all sorts of examples, numerical examples. So you need to read about this. Okay? Didn't you? What?
Yeah.
What? Yeah, I just eliminated it? I just got rid of something you wanted to see? No.
It's the last slides. Why we are
I can get them back up here. You want me to?
about
How can I get over? Okay, let me go hold it. Oh, I got rid of the whole damn thing. Well, let's see. Can I do it here? Here?
we don't not have to use slides.
Okay.
I'll just ask you
Okay.
because we have two E's
Yeah.
and we're assessing up to E1. When we are doing that, we are assuming like X is hard. If both E equals to 1 versus both E equals to 0.
Well, alternative one, I said first test the EWs and then test the EE. And I didn't even do that. I just said, suppose when you do it, everything drops out. I didn't do the second part.
Yeah, but we're assessing the confounding.
Well, that's alternative two.
Well, we want to assess
Oh, even for alternative one.
yeah.
Alternative one, you're assessing confounding, but I dropped both kinds of product terms. Because I say when I try to do them, each one at a time, neither of them stay there.
Yeah. My question was really easy. Because when you're assessing the confounding, you're assuming like E1 each equals to 1, E1 each equals to 0.
I could have done something else. I didn't have to do 1, 1 versus 0, 0. I could have done 1, 0 versus 0, 1. But if I do that, that's not as interesting as very, very strong versus very, very weak. Yeah, that's why I did that. That's an example. And a lot of people do it that way, but if you don't want to do it just that way, what you could do it is you could do it that way, and then you can do it any of the other ways. Then you got more work to do. You might get more than one different best model. In other words, when you do 1, 1 versus 0, 0, you get a certain best model. When you get 1, 0 versus 0, 1, you get a different best model. You know, so then you're more into more trouble. You know, and then it's more debatable. I mean, that's what I'm saying. Why do you want to be in this class? Because, I'm not really saying that. But there's a lot of issues like this that aren't that. There are ways to try to deal with things, and that's one way that people deal with it. They say, I got these two variables. Let's compare somebody who has both versus somebody who has neither. That's the two extremes. The one extreme versus the other extreme. If there's nothing going on there, there's nothing going on in between. Now, that doesn't automatically be true, but
Yeah, for me, it's way more about why we are assessing. We have both together, the stronger impact versus none. Then
that's
they
the
have-
extreme.
Yeah, then they have E1 interaction, which might be eliminating some of the impact. Maybe they cancel each other out.
Well, they might. I mean, you might miss something with that.
Right.
There's no guarantee that you're not going to miss something, but it's just a point of view about it. Let's take the extreme.
So the chapter 8.
Chapter 8's the one that I talked about.
Modern epidemiology.
Logistic regression, Kleinbaum and Klein. Don't read modern method and expect us to learn anything about logistic regression. You might learn a lot about other things, but not about logistic regression. They don't get into that. Okay? Andre, did you get my thing that I sent you?
Yes, thank you very
You
much.
did? Okay. I don't know if that helped.
That was more of a overlook,
That was overload.
the calculation. So I was aware of the formula, but when I did this formula with Lauren, and so we're gonna figure out that I was not multiplying, I was actually adding, and that was not.
Okay.
But anyway, thank you very much.
Okay.